Hi, myself Dr. S.K. Bushra. The subject is physics. The topic is electrostatics. And the level is class 12. Chapter 1, Lesson 3, Charging by Conduction, etc. In this lesson, we'll discuss the following. Charging of material bodies by conduction, distribution of charges in conductors, and finally, some interesting electrostatic experiments. The first topic is charging by conduction. Charging by conduction is also referred to as charging by contact. So let us begin. Charging by conduction. Bring a charged conductor, we'll call it A, and allow it to touch a neutral one, we'll call it B. Here, a negatively charged conductor has been used. Some charges, electrons in this case, will migrate from A to B. With respect to the asterisks, the migration of charges from A to B, as well as the extent of migration, could be explained in terms of electric potential. We'll discuss it in a later lesson. Now separate the conductors. The newly acquired charges in B distribute themselves on its surface as per certain rules. Meanwhile, charges in A settle at some lower value. With respect to the asterisks, we'll discuss these rules very shortly. An observation. Had A been positively charged initially, the conductor B would have been charged positively. Can we charge an insulator by this method? As in the case with induction, this method fails with insulators. Charges do not migrate to an insulator unless it is rubbed vigorously with another material, of course an appropriate material. A contact is no substitute for a vigorous rubbing. However, a charged insulator can charge another insulator by a method called charging by lightning. With respect to the asterisks, we'll discuss it in a later lesson. Where do the charges reside in a charged material body? First, let us talk about a conductor. Charges always reside on the outer surface of a conductor. Why? We know that like charges repel one another. The charges in a conductor always try to minimize their mutual repulsion by staying as far apart as possible. This is accomplished if all of them move to the outer surface of the conductor. The surface density of charges, sigma, that is charge per unit area, on the surface of a charged conductor is not, however, uniform. Sigma is a Greek letter usually used to denote surface charge density. Sigma increases with increase in the curvature of the surface. Regarding the asterisks, for explanation, please wait till we take up electric potential for discussion. A spherical conducting surface has the same curvature throughout. So, sigma is constant over a spherical conducting surface. Remark, two spherical conductors of identical radii, but one solid and the other hollow will have identical sigma. But sigma is variable over irregular conducting surfaces. Sigma increases at the sharp corners of a conductor, as shown in the figures below. In the figures above, The charges are shown outside the conductors for the purpose of illustration only. In an insulator, charges are immobile. So, charges produced therein by rubbing will remain localized. Now, a little bit of history. Thales of Milesia knew that amber rubbed with wool or silk cloth attracts light objects. The discovery of Thales of Milesia dates back to 600 BC. Thales of Milesia was a Greek mathematician, astronomer, and a pre-Socratic philosopher from Milesia in Ionia, Asia Minor. Is a picture of a piece of amber. In fact, the name electricity has been derived from the Greek word electron, which means amber. Let us take up the discovery of Thales of Milesia. We have already learned that the amber becomes negatively charged when rubbed with a piece of silk or woolen cloth. A charged sample of amber could cause electrostatic induction in a nearby body. Let us assume that the nearby body is either an insulator or an insulated conductor. In induction, induced opposite charges come near to the inducing charges, while similar charges move to the far end. On account of the proximity, the attraction between the dissimilar charges in the two bodies exceeds the repulsion between the corresponding similar charges. So the net result is attraction. Therefore, induction always precedes attraction. Obviously, the amount of charge produced in a piece of amber by rubbing could not have been too great. So the resulting attraction is also not too large. Hence, it could attract only light objects. One can easily replicate the experiment of Thales of Milesia. Rub a dry plastic comb with a piece of woolen cloth. Bring the comb near some small pieces of paper. The pieces of paper will jump to the comb and stick to it. Can you replicate the experiments of Thales of Milesia with a metal comb? It is not easy to charge a conductor by rubbing. The charges produced therein usually escape to the earth through your body. If you decide to hold the metal comb with an insulating handle so that the charges may not escape to the earth, even then, the distribution of charges all over the surface will greatly dilute the attraction by induction. So the answer to the question is no. Let us perform an experiment. Suspend a small polystyrene ball by silk or nylon thread. Bring a charged rod, say a negative wooden rod, near the ball. A wooden rod becomes negatively charged if rubbed with a piece of silk cloth. We'll observe that the ball is attracted towards the charged rod. Now, what is the charge status of the polystyrene ball? One possibility is that the polystyrene ball is positively charged. As the negatively charged rod approaches the ball is attracted towards it. There is another possibility. The polystyrene ball is neutral to begin with. The presence of the negatively charged rod causes electrostatic induction in the ball. And then attraction takes place. There is one more twist to the tale. The polystyrene ball moves away from the charged rod. What is your conclusion? The polystyrene ball is negatively charged to begin with, and this is for sure. And a negative wooden rod repels the ball. We have learned one important lesson from this experiment. Repulsion is the surer test of electrification of a body. Now a few words about gold leaf electroscope. It is an instrument to detect the presence of electric charge on a body. Two thin flexible gold leaves are attached to one end of a metal rod. The other end of the rod terminates in a disc or a ball. The rod with the leaves are enclosed in a glass enclosure, usually open at the bottom and placed over a conducting base. If the leaves of the electroscope diverge in presence of a body near its disc, then the body must be charged. In presence of a charged body, induction occurs in the electroscope rod. As you can see in the figure, induced charges diverge the leaves by mutual repulsion. A charged balloon sticks to a wall. Why? First, the induction occurs in the wall, then the consequent attraction holds the balloon. Why are you talking about a balloon in this example? Because the force is not big enough to balance heavier objects. Take a charged balloon close to your head. Your hairs will be raised. Why? The charged balloon causes induction in your hair, and then consequent attraction raises your hair. And you end up having a hair-raising experience. We have come to the end of the lesson 3. In the next lesson, we'll study Coulomb's law of electrostatics. Thank you.